Wireless sensor networks are currently in use for several applications, including environmental monitoring and intelligent transportation systems. However, there is some disadvantage for traditional digital sensors that are incapable to meet this demand because of their high power consumption, high complexity, and the use of non-biodegradable materials. Our purpose for this design is to develop low-power, low-cost sensing devices. Then we can manufacture them using biodegradable materials. Compared to the traditional digital sensors, we use a single field effect transistor to encode the value instead of using the analog to digital converter. The same goal can be achieved with lower power consumption and lower complexity, which is the technique of analog joint source channel coding. To realize JSCC in an energy-efficient manner, we propose to use the input-output characteristic of a single MOSFET device as the space filling curve for JSCC. Through this novel approach, we are able to achieve power of the order of a few tens of microwatts for the encoding circuit. We are able to achieve this by working fully in the analog domain and by avoiding power-hungry analog to digital converter and microprocessor, which are used in digital sensing modes. We divided our system into 3 tiers, and each of them work independently. Tier 1 analog sensor nodes perform sensing and communicate with the digital cluster head via analog joint source channel coding. Tier 2 digital cluster head perform computation, processing and control, and digitally communicate among themselves and with the Tier 3 fusion center.
The fundamental power of analog joint source channel coding (AJSCC) lies in its ability to compress 2 or more sensor signals, such as temperature and humidity, into one signal with controlled distortions. In general, AJSCC is utilizing a low complexity technique which is used to reduce the power consumption and cost. The most basic kind of AJSCC uses channel mapping as its encoding method. From the diagram, VT and VH values can be indicated by X and Y labels, which form a group of data pairs. Then, through setting the limitation on X label and the delta on Y label, a rectangular line is formed, and the coordinate XY is projected onto the line, so that the length of the line can represent its position. In another word, each data pair is transmitted into a single length. 2 different pieces of information are converted into a single piece of information. Thus, if we have only a capacity to store 100 pieces of information, then channel mapping enables us to store 100 data pairs. Without this encoding, we can only store 50 data pairs. When rectangular form cannot satisfy the requirement, there are many other choices, such as mapping with Archimedes spiral. This technique can be used as a bandwidth reducing mapping in a joint source channel coding system. The combined point of 2 Gaussian sources is mapped onto a double Archimedes spiral, and the squared angle from the origin to the map point is transmitted as a channel signal. Each data pair is transmitted into a single angle in this case. However, through this project, we are using a new method instead of the classical ways, which is related to MOSFETs. Like other AJSCC mapping schemes mentioned before, the MOSFET design achieves better trade-off between channel noise and approximation noise and can be built by all analog components to achieve an ultra-low power realization of AJSCC. One more reason why we select MOSFET-based encoding at transmitter is that it should result in a unique mapping. Given the desirable property of a space filling curve, we propose the idea of using the IV characteristics of a MOSFET in saturation region as the space filling curve instead of rectangular parallel lines. Through this technique, it's able to achieve a few tenths of microwatt power consumption for the encoding circuit because the analog sensors that comprise the lowest tier of the wireless sensor network only sense and transmit, but do not perform any processing like traditional digital sensing modes. Sensors won't need to be powered down, increasing the temper of the system. Furthermore, we would like to introduce the transmitter antenna part in detail, about how it can collect and quantize data in the wireless sensor network. In this case, the singular MOSFET converts two groups of data to a single group, or we can say that the values of VGS and VDS are transmitted into IDS, which will increase the storage capacity. Here is the detailed diagram about this circuit in LT-Spice and breadboard, which does the proper quantization of gate-to-source voltage. We select 125 voltage as our input with 0.5 quantization level. These are the simple voltage dividers. Start from 125 volts with 0.5 quantization level, which provide power source to other chips, and the output is selected from one of these values. These are LTC1440 analog chips, which do the comparison with voltage source. The outputs of these four chips are the control inputs in the following steps. This control part is combined by LTC1047 and 2x1 muxes. The main function of this is dividing the input, the original VGS, into integer and fractional parts, and decide which mux will be selected to generate the final output VGS quantized. Here is another control part, which do the comparison between the fractional input with 0.25 and 0.75 separately, due to the 0.5 quantization level requirement. It can decide the channel used in the output part, so when it works with the previous control part, the final output is selected. Now is the output part. It's controlled by the whole system and generates the final output and transmit it to the singular MOSFET. As we can see in the diagram, the VGS is quantized properly, and this will be a short video to show how it works on breadboard. Then, when we collect the IDS values and plot it with corresponding VDS and VGS, we got a diagram of MOSFET saturation region property. Here is the pre-circuit built by group 64, which does the proper quantization of gate-to-source voltage. We select 125 voltage as our input with 0.5 quantization level.
During the process of signal transmission, we let the current generated by MOSFET go through frequency modulation block, which can transform the signal from time domain to frequency domain. Then we add white Gaussian noise to the signal to simulate the noise during the transmission. The following graph shows the simulation we made for the transmission process of the signal. At the receiver, we transfer the signal from frequency domain back to the time domain and decode the signal by using MOSFET, analog joint source channel coding, and slope matching technique. Peak frequency is mapped back to AJSCC voltage, which is then decoded to sensor values. In order to test the functionality of the system, we simulate three different scenarios for signal transmission. The first one is the scenarios of countryside, which have less obstacles and less reflectors. The second one is more advanced, which simulates a scenario in the city, which have more obstacles and interference. At last, we simulate the signal transmission in a moving transmitter or receiver, which include the Doppler effect. We try the speed of 250 km per hour and 5 km per hour. We do a convolution between channel gain and the transmitting signal to generate a new current signal. To calculate the mean square error, we vary the signal noise ratio from -100 to 0 dB, the x-axis in the plot, for varied bandwidth from 50 to 500 kHz as the y-axis in the plot. From the plot, we can see that in any bandwidth, The mean square error drop-down at signal noise ratio is negative 20 dB for every scenario, so we can say that this wireless communication system is working functionality and properly at different scenarios. Our system can be used in simple and complicated environment and terrain. From the result, our system is working as expected in terrestrial with a different model of terrain.